Welcome everybody to this webinar from the American Nuclear Society's Risk-Informed Performance-Based Principles and Policy Committee, RP3C we call it. My name is Prasad Kadambi and I'm chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We've been calling these methods RIPB approaches, and the Nuclear Energy Innovation and Modernization Act has incorporated the idea of RIPB in statute, and this gives us a lot of opportunity to pursue modernization across many fronts. There's a lot of guidance available on RIPB approaches, but most people have not had reason to become familiar with the guidance, because the conventional approaches still dominate most things that we do, including standards development. Right now, I think ANS can be considered as a knowledge center for RIPB. RP3C initiated these community of practice webinars on RIPB to enable practitioners of these RIPB approaches to share their knowledge and experience. We've been scheduling these on the last Friday of every month, and we appreciate people making the time to join us. Today we will hear about a topic that is very important, and yet we haven't heard much about how RIPB is used in this whole important area of digital instrumentation and control. I'm very glad that we have an industry authority in this area from EPRI to give us this month's presentation. Matt Gibson will introduce himself and also make the presentation. Matt, please go take it away.
Sure, thanks, Prasad, for the invite to speak. Today, I'm going to cover research and products that EPRI has produced to address the new paradigm of risk-informing and performance-based solutions for I&C design. So we'll get started, and it's good to see a few familiar faces out in the participants list, and hopefully we'll get some questions in chat here in a few minutes. A lot of you are familiar with EPRI, so I won't, belabor this too much. The key thing here is EPRI is independent and collaborative in nature, so we are out trying to push the envelope a little bit, provide thought leadership, and maybe do some things that move the needle a little bit on different items that need to be done. And risk-informed and performance-based is undoubtedly one. I mean, you get to see these slides in another venue, so I won't belabor myself much, but I am a licensed professional control engineer and a certified cybersecurity professional. Been in the industry a long time, got my start in the military. I've done everything from being a technician to being a IT, IoT manager, and a fleet digital architect in my career before joining EPRI in 2013. So as EPRI, I have pursued the research in human factors, cybersecurity, and digital engineering in general. And so much of this framework have been things that EPRI has developed in the last few years. So we're going to talk about the EPRI Digital Systems Engineering Framework. It's kind of a cool thing. Digital is different. I mean, you've heard that, but here's why it's different. you see all these instruments and different things, and this environment you see on the left has been optimized for the traditional instrumentation of the time when these plants were, the legacy plants anyway, were built. And so now all that information and possibly all that control can be done on one yellow wire. That's really a change. That's really a sea change. So EPRI looked at that. And we said, well, the nuclear industry is really not using modern processes. And so, and we also have fragmented processes. And if you've been in the industry a while, you're probably aware that our engineering and many of our other processes are organized around prescriptive, audit-based checklist sort of things. And we have individual processes to address individual, at least in the US, regulatory positions. We also understood after doing our research and looking at other industries and the state of standards in other industries, that really to move the needle along, we needed to develop a complete framework that handled all elements of I&C design that you would see going forward in a modernization or in a new reactor design. So everything I'm going to talk about applies to upgrading old reactors, as well as building new advanced reactors and modular reactors, and is also regulatory agnostic. So these processes can be used worldwide. EPRI membership is about 50% non-US, so all of our products, we strive to make them, universally useful to our members. So this framework has 4 pieces. The first of them is utilize industry standards. Now, we're not talking about necessary nuclear standards, because our research really tells us that we need to denuclearize I&C. Why? Because other industries have surpassed us in industry standards for safety-related industries that actually do a better job than what our nuclear-specific standards may have been able to achieve in the past. So these frameworks are built around IEC 61508, IEC 61511 for your functional safety, 62443 for cybersecurity. As you'll see in another slide, we use IEC, ISO, IEEE 15288 and 289 and 12207 to round out the systems engineering, which is you'll see next, the systems engineering framework. So this is a systems engineering based framework. If you're not familiar with that, you can go to INCOSE, INCOSE.org, and get familiar with that. But systems engineering is the modern way of doing engineering. So the next thing on the list of the pieces of our framework is the use of systems engineering. This brings everything into a single engineering process. And why is that good? First off, people are learning a common way of doing engineering. It's a common philosophy. It's well understood. It's very successful. That's the other part. What systems engineering does is takes any requirement, whether it be a regulatory requirement, a system functional requirement, a stakeholder requirement, brings it in as a requirement. So the process is the same. So we don't have an independent process for one kind of topic and a different process for another kind of topic. It's all the same topic. You bring it in to a common requirements funnel, if you will, and then you implement through that single process. Risk informing. Most people who studied engineering and practiced engineering always have to do trade-offs. Nothing's perfect. Risk informing can allow that because now you're essentially evaluating all the things that could happen. What's the value of certain design elements and features? Central to that is hazards, risk, and reliability analysis. So that's the third leg, is to have those features in the framework. The last one is a capable workforce. These are new ideas for the nuclear industry in many ways, especially in the structured sense that you see here. And so it's critical for the success of this that the workforce be trained, and mentored, and more than just trained. This is these kind of kind of sea changes, and I'll speak to that in a few minutes, aren't easily achievable simply by having a new process for someone to follow. You know, we're not going to get there by following a procedure, actually. That's the framework. That's the 4 pillars of it. Industry standards, not necessarily nuclear industry standards, but safety industry standards, use of systems engineering, risk informing that engineering, and developing a capable workforce. Now, how does this fit in? Well, I'm talking about EPRI products now. And EPRI products in this worldview are implementation level products. This is what you actually do to achieve the things you want to achieve. In order to make that work out right, there's an implied upper level framework that takes policy, that's regulation, company policy, whatever, wherever you're getting a policy from, creates an objective criteria. Now, I want to point this out, because this is the risk-informed performance-based community of practice, is having a objective criteria connector between your regulation, and we're assuming here that your regulation doesn't try to actually do engineering for people. Sometimes that happens, but let's say that your policy and regulation set true policy and regulatory requirements, and then objective criteria, which can also be from a regulatory agency, but can also be developed by other folks, connect that policy to an implementation level process. And these objective criteria are going to come into play because those are the ways you're going to judge a performance-based process for whether it works or not. That's going to be one of the challenges you have with performance-based, is how to audit it, how to know if you're getting the right thing, and you know how you're doing assurance activities. So this is the model. So EPRI does this because this can be used all over the world. I mean, we're not regulatory centric, so we can take this method and go to the UK, to China, Europe, other European countries, Africa, South America, and still use it in the regulatory regime that you would find in those countries. When we've showed this to O&R in the UK, you know, which you haven't seen it all yet, but you will in a minute, they really are, you know, intrigued with it because it helps you produce a structured safety case. You can follow the objective, the policy, the objective criteria, and the implementation artifacts that you see. All right, so let's just dive into it a little deeper. Again, this is, you know, EPRI's doing continuous research on this, and this whole process has taken about 10 years maybe to get to the different pieces as they've been developed over time. We did reliability research about what makes something reliable. We pulled almost 2 billion hours of reliability data through safety integrity level certifiers. These are people who certify equipment, platforms to IEC 61508, which is widely used in the process industries for safety critical. And when we did that, we found that really you have 3 reliability layers. You have the platform, the integration, and application layers. Each one has different reliability dynamics. And of course, each one of them has progressively, as you work from platform to application, you have less maturity. Applications being the least mature because they tend to be specialized for a particular application, whereas platforms are common. So you can make different conclusions about reliability depending on which part of the system or the system of systems you're in. Here's some axioms for reliability. In our research, you know, design and random failures, cyber vulnerabilities, human reliabilities, systematic failures or errors are all the same thing from an engineering perspective. There are hazards, there are elements of your design you have to deal with, there are challenges to the design. And so people talk about CCF a lot. Well, you know, a CCF is just another error and just another failure. And so our research would tell us that, you know, you should not simply go looking for CCFs. You should be looking for reliability issues in your system. Why? Because your systematic and random reliability of your system are inversely proportional to the likelihood of any event. So if you increase your reliability of the system, systematic and random, you're going to reduce your CCF likelihood tremendously. You must first have a failure before you can have a common cause failure. So again, you're getting back to, if you make your system reliable from a systematic and a random failure point of view, your likelihood of a common cause failure is vastly reduced. We can't ignore that. We have to balance, cost, likelihood, and consequence in an equilibrium, because, we don't have unlimited resources. Like any good engineering, we have to take the best idea and implement it. So you see here a little bit about the framework's values. Okay, so the big thing to take away from this is it's a modern process. It desires to get to better results in less time and less cost. Better results. Let's just make sure we remember that. Regulatory and reactor technology neutral, single process, covers everything, cyber and human factors. It's risk informed and performance based because it really uses risk as for insights, and it is focused on the outcomes, not the outcome is what matters, the performance of the design that you ultimately produce. That has a lot of value. One of the things to reiterate in this value is it eliminates separate processes like the SQA process, all built together in one process. I have a little note in here. I put this PB in here. Structured results allow for higher assurance and fast reviews. This is true, provided there's a change in how we approach reviewing performance-based outcomes and how we perceive the information we get as providing high assurance. I'll talk a little bit about that in a bit. This is the integrated framework in a nutshell. You have all the topics that the framework covers. The core process is the digital engineering guide, the DEG as it's called. Systems engineering based, performance based, it's risk informed. The process. We use these international standards. I've covered those already. The US industry has standardized using the DEG through the Nuclear Promise Program. They've created a procedure, NISP E-N-O-4, which U.S. utilities use today or are using. They're in the middle of their implementation right now, are transitioning to use the DEG to do digital design under the standard design process. There's also an element of a optimized digital engineering organization. We can chat about that if anybody's interested. That's also an attachment to the DEG that explains our benchmarking and other industry observations. This is a modular process. You see the DEG is the core, but we also have hazards analysis. It has CADS, that's our acronym for it. Uses system theoretic process analysis and fault tree integrated together. Our DRAM product handles the reliability, software and hardware reliability of a digital system, both systematic and random and environmental. The TAM handles the cybersecurity assessment at any phase. It's built right into the different phases of the design process. HFAM is a risk-informed human factors process. It integrates HFE and HRA together. These are all in production, so they're at least their revision zeros are done and out for people to use. People are using them or preparing to use them. EMCAM, it will come out next year, and that's an risk-informed electromagnetic compatibility methodology. So I'm going to pivot a little bit and talk about our hazard analysis. This would be HAZCADs that and our sub-processes that go along with that. Almost 10 years ago, EPRI did some research on effective hazard analysis methods. We discovered that, no one method works perfectly. So, but in our testing, so we just to give you a background, we took these methods, we presented blind teams, blind to the problem, not sightless folks, but blind to the problem. We did experiments, we gave them these scenarios and said, can you find what's wrong with this? We knew what was wrong because we used real industry events that we had root causes for. And we watched them go through it and try to find the problem just with the engineering information that would normally be available. Has STPA come out one of the clear winners in finding those problems. And we looked at it and said, we can synthesize this into a process, which we did. And our HAZCADS process implements step 1, 2, and 3 of STPA. We identify losses, we identify system hazards, and we identify unsafe control actions. Now, for each unsafe control action, we need to find out, we create loss scenarios. There can be loss scenarios caused by all sorts of different causal factors. And those different topical processes that you saw on the previous slide address those. Hardware and software reliability, cybersecurity, human factors are the big ones. And then, of course, electromagnetic compatibility. What we do, and this, I don't have enough time to go into super detail, but I'll hit the high points here. When we dove into this, and we did a lot of back and forth and experiments, we went down a few paths that we discovered maybe weren't optimal, and then we went down other paths that were very successful. We did tests. The short story there is using risk insights in the design of a system is not the same as using your PRA that you have today, because your PRA is an assessment risk. It's assessing the design after it's already done. And it doesn't answer the design question. And when you consider that the systematic areas in particular that we're faced with, software, reliability, cybersecurity, some human actions, they don't lend themselves really to probability or frequency of failure exactly, and all sorts of things. So what we use in this process is the idea that you can take an unsafe control action, which we mentioned in the prior slide, and you can do a risk sensitivity on it using your traditional risk sensitivity tools like RAW and Fussell-Vesely. And ultimately, we can also inject put these as basic events in your fault trees. And we're not measuring what I would call the assessment risk. What we're doing is measuring the sensitivity. Why? Because the insight you're looking for is to know what design features you need to put in based on this risk sensitivity of your design. So that's the risk-informed element here. Our digital engineering guide, which you saw earlier, creates the design. We bring that information to HAZCAD, we do hazards analysis on it. The downstream processes take those risk reduction targets, which are based on that sensitivity analysis, along with the insights that come through doing the hazard analysis. Downstream processes then find loss scenarios of why this would happen, what element of the design would cause this. It creates control methods which are implemented as requirements, and it iterates back into the digital engineering guide process. So systems engineering, very iterative. This diagram is a little plainer to see because this is the conceptual phase, and you can see how we take the design from the conceptual phase. We view these processes as diagnostic in nature because you're in hazard and risk sensitivities with HAZCADs. And then for the different topical areas, we do loss scenarios, again, based on those RRTs. And then we produce scored control measures, revised requirements, all that reflects these diagnostic results. So actually your design is beginning to converge, it's got this feedback loop. And this is a key element of saying something's performance-based, because we're scoring the control measures and measuring via hazard analysis the the quality of the design or the outcome of the design, or whether it has an issue, doesn't have an issue, if it needs other things in it. So here's where you're combining your risk insights with your performance-based insights, performance of your design. You know, is the design a good design? What's the outcome of that design? This iterates from concept phase into design phase. This gives you a little idea, you know, these risk reduction targets on an ABCD scale. So because they're qualitative in many ways, you can see is your risk reduction target, if your risk reduction target was an A, you would need to meet a SIL or systematic capability of 3 per IEC 61508. And if you were above that, if you needed more risk reduction than that, you would be challenged to eliminate the hazard, do something different entirely so that there's no hazard there, or substitute it with a less onerous hazard. Different diagram shows you sort of that there's a risk reduction band that you can actually create a bad design that's outside that risk reduction band, and we require to do something about that before you apply, you know, your normal design features to it. Now, we don't use Red Guide 1.174 as a thing, because, you know, again, we're regulatory agnostic, but we did this overlay from 1174 just to illustrate that, for instance, if you did a risk sensitivity and your CDF or WRF was at a certain level, it would indicate you needed a risk reduction target of a certain amount. In other words, you need to reduce if you had an A, you would need to reduce your risk back down to your threshold. Remember, this is design. This is feedback for the design. This is not the risk of the system. This is the potential sensitivity of the system to a failure, right? So this gives you insight on how to bring what things you need to apply to that system or that design to bring it back into an area where, you know, the real risk of it would be proportionally back at the baseline. A little tricky concept to, you know, get your head around without some training there, but I'm sure you guys kind of get the idea of that. Because again, this is a qualitative application of a risk sensitivity that we do. This can be used with any metric, not just CDF and WRF. The process allows you to create your own metrics, which you would for economic loss, generation loss, personnel safety, reputational loss. This is just examples of top events that are, you know, important on everybody's mind for traditional reactors. As you get into new reactors, you know, the relevant top events or consequences that you want to look for could be different. Now, in the US, the DEG has been directed to be implemented through the NSIAC CNOs using Efficiency Bulletin 1706. And the industry is in the process of doing that. You can see here that we have procedures, IP-ENG01, industry standard procedure in the United States. The NISP EN04 has been added to that. That's the digital engineering procedure. The DEG, the digital engineering guide, and the subsequent other methodologies are linked to the NISP EN04 for use by the industry, and they're in the middle of implementing that. We've trained 500 plus practitioners to date on the process. So, you know, everybody cross your fingers. We should wish everybody luck on that. This is probably the all-in-one slide. You can see the DEG, HASCAS, DRAM, those things, key elements. But what to take home here, I think, is that NEI has chosen to use this framework to go forward with proposals via NEI 2007, NEI 1706 that implement these ideas. Matter of fact, 1706, which allows IEC 61508's SIL certification process to be used without further analysis in a commercial grade dedication, is progressing. It's essentially been approved and will be issued as a red guide in the fall, red guide 1.250. 2007 is now in is sitting waiting on the rest of the industry and the NRC to finish with some policy changes that they're working on. So assuming that turns out, however that turns out, NEI will then submit 2007 as the process to achieve those regulatory goals, risk-informed regulatory goals in the new policy. And 2007 is based on these products. So you got that tie-in. We've got pilots being identified for 2007, and workforce development, implementation resources, are in play going forward to do this. Now, HASCAD's DRAM and HFAM, these have all been various revisions, but the current revisions were delivered in mid-2021. Constellation is currently piloting this again in parallel with doing some other things. We did proof tests of these. Last year, we created a simulated plant design change in over a 3 months period. We had a group of participants work on that design. We analyzed their performance and their results. So that's the state of the union here for the framework. I want to share with you risk-informed and performance-based challenges, because this is a community of practice, and you're trying to do this on a wide scale. Your biggest challenges are work culture biases. Okay, so when you go to performance-based, risk-informed and performance-based, just a really radical departure from what people are used to, checklist QA kind of things. And quality concepts based on procedure adherence. Well, we get the fact that our procedures, you can't create new, can't innovate in that situation because your mindset doesn't work, and you can't reap the benefits of risk-informed and performance-based that way that you guys are saying are great things to do, which I agree with. It really changes how your engineers interact with management, auditors, and regulators, because management, auditors, and regulators today in the nuclear industry are looking for checklists. They're looking for, I need to audit somebody against a process or some list of things, and performance-based processes have to have a new way to do evaluations of whether you got the right outcome or not, or whether your performance is what you want. You have to have performance objectives, and the industry's struggling with that. Today, we're in the middle of implementing the DEG. The engineers are feeding back to us, their managers can't get their heads around what happens when the engineers are doing risk-informed and performance-based things, and they don't really know what to do with that, actually. Right? How do I manage that kind of a process? How do I know if it's getting the right results? Another thing is, as you go into performance-based things, it increases the responsibility of your engineers and your risk professionals. Now, this is performance-driven now, right? Performance-based, not procedure-driven. So you can't be successful simply by following a procedure. You have to actually perform. So everybody has to agree on what good performance or outcomes look like. It requires active, team-based, participation-based engineering. That means people really have to collaborate and share and brainstorm and create a final product, whatever it is, that has taken into account all these systems engineering-based inputs that are required for high quality design. Last one to share with you, the industry workforce knowledge, skills, and abilities are misaligned with risk-informed performance-based. People don't know how to do this. Engineers, management, regulators have to transition to a risk-informed and performance-based mindset for you to be successful. Your nuclear practitioners need better systems and technology skills, better performance tools. We need to move into an enhanced systems thinking kind of idea. Going to take senior leadership to move this along at a crisp pace if we want to achieve anything with it, and workforce development is needed. Yeehaw. Now, I do have, you know, something else to quickly share. This is not part of the framework, but it's an outgrowth of it. So we created this framework. We've tested it repeatedly for several years scientifically. I mean, you know, blind studies, all that sort of thing. We understood that we have a risk-informed design process, which is all good and dandy, but now what do you do with those insights with your regular assessment PRA, you know, the thing you use on a day-to-day basis to decide if your risk is going up and down? And so we've kicked off a new process, project, because again, the process you just saw is not directly something that for instance, an assessment PRA would be able to use. We did some research and found out that people were all over the place on how they handle digital in their PRAs, you know, their assessment risk models. And so we're working on that. And we're trying to bring the insights that we got from HAZCADs into basically probably a new product for EPRI, you know, that would be something that we would enhance our current Phoenix or CAFTA products to allow us to push that back, some of those insights back into the PRA, and have an assessment PRA that substantially correlates the design decisions that were made. You know, you can't design a system and say it's, you know, low risk based on this, and then subsequently say in your assessment PRA that it's high risk, or that a change to it would cause the risk. You can see where those would be hooked together. And so we're working on that, trying to bring, because remember, our design PRA also brings cyber, systemic issues, software, human actions, although we do have today human reliability analysis, but we're integrating that more closely to the design process into a PRA insight. When again, we're starting with HAZCADs, outputs, you know, trying to figure out how to bring those insights forward. Let's see if there's anything good to say here that you can't read for yourself. Ian, trying to make it not so complicated, but it is going to involve, you know, being able to take, you know, qualitative and sensitivity insights and making them relevant to your assessment PRA. Again, we're getting back to CDF and LERF not being the only metrics of importance. You can damage your plant. You can, even if it's safe, you can have loss of generation, just routine loss of generation. And your advanced reactors are going to have different metrics potentially. So we got to think through that. You know, INC risk may have limited use for radiological risk perspective, because one of the things we're finding is it's not that sensitive, maybe depending on the reactor design. So these other factors need to be kind of, to make risk valuable, risk insights valuable, they have to be used for other things beyond just radiological risk analysis. This also brings the risk analysis, integrates it with other plant processes, because now configuration control, the assumptions you made, it's not just about the reliability of components you get from a database. Now you got to pay attention to, you know, are all the things you said you were going to do still in effect? You know, what's your process for that? We have a lot of good processes. These need to be integrated and made where they would come together potentially. We're trying to make sure that any new model captures cause and effect, because without that, you know, it's not going to be as useful as it would be otherwise. We have data from Korea and other places, and we're trying to just, you know, getting those best practices that we see for digital into this mixing bag, so we can have a clear proposal. We're going to put that out in a white paper maybe later this year as we hurdle toward figuring out, how this would actually look in practice. We're looking for challenges to it, so if you're in any way interconnected with those reviews, challenge those. And that's about what I had. So I think we can open it up for questions.
Well, thank you very much, Matt. I don't see any questions in the chat, but people are welcome to go, to unmute yourself and ask a question if you wish. Anybody would like to do that? You can raise your hand in the in this Zoom platform under I think reactions. So let me take the opportunity while people are maybe thinking about a question. I'd like to ask you, Matt, where do considerations of defense in depth, especially which is important for the nuclear industry, where does that fit into digital INC design, and how it is how defense in depth is implemented in digital INC design?
So defense in depth is just a general engineering concept. Let's just make that clear right now. That's something anybody designs something kind of is going to do that. So in the digital engineering guide, which is systems engineering based, is going to do interface analysis. It's going to do functional analysis. It's going to do functional allocation. We have a concept called relationship sets, which is again beyond what I can talk about in detail today. But all of these help you model your architecture. Okay, so once that architecture is done, which will include some design defense in depth at the INC level, but it will also take credit for defense in depth at the facility plant, outside the INC system. When we do our hazard analysis, the effectiveness of that defense in depth will start to reveal itself, because then you will see, well, this could happen, and what would prevent that, either within the system or with that, exterior to that system. And then we create new design elements or control measures, we call them, because we kind of standardize on that term. That's how we're controlling the issue that's discovered in the hazards elements, and we push that back into design and the requirements. So at the end of the day, you will have a balanced design that has a mix of system and plant level defense in depth, internal defense in depth, that addresses specific hazards. So there's nothing prescriptive about that. It's just, if you have a hazard and defense in depth helps you with that, reduces the likelihood of that risk happening, then of course it happens. That's really how that's done. So you get your defense in depth, and you go within the system through the design process, and you correlate that with your overall plant and facility level defense in depth features, which might be in fluid mechanical, electrical elements. You coordinate those through your hazard analysis to see if you need more or less internal defense in depth. Wow, that was a long answer, but best I can do.
Just as a follow-up, before we go to Ian Jung, who has a question, I'd just like to ask your treatment of defense in depth. Has that been reviewed in any way by NRC staff? Have you had any feedback?
I think that type of thing will happen as the new policy matures. The idea of what I just described is in NEI 2007. I mean, it was the EPRI process, but they put that in 2007. And the staff decided that they could not review 2007 until the risk-informed changes of policy occurs. So we'll see. All right. Because again, in order to reach these conclusions, you have to be able to balance risk insights, stuff that's really not 100% allowed today in U.S. regulatory space. And so we'll see.
Okay, let's get to Ian Jung's question. Are there any interest from new advanced reactor applicants to use the DEG process for their INC design?
I would say there's some interest. Most of the advanced reactor developers are members of EPRI. We are familiarizing them with these techniques, these risk-informed and performance-based techniques. And there is interest because one of the things they're grappling with is, you get advanced reactor. Well, today, and I think advanced reactor is going to be the same way, they're licensed to the end user. They're not licensed to the manufacturer. So, it's like buying a car. You're going to get to tinker with it and be responsible for maintaining it and modifying it and put repair parts in it and upgrading it when it gets obsolete, or is that going to be the original equipment manufacturer solely responsible for that? And they're grappling with that because this process, if used in the original design, can flow through to the licensees. Some of them are more or less along in their design, so that has something to do with it as well. But yeah, there's a lot of interest, especially the risk-informed and performance-based part of it.
Okay, there's a question from Greg Hudson as a DID follow-up. What is the strategy for addressing software common cause failure?
Well, I covered that a little bit in the slides. Software common cause failure is a software reliability concern. And so our research has told us that proper systematic controls limit the likelihood that you will have a CCF because you will have the less likelihood of an error. Again, this is a big thing to swallow, but it's all based around the international standards, IEC 61508, which sets constraints on the design for the software to improve its reliability. And so pulling those techniques into this process is probably one of the success factors there. That DRAM is the product in particular that has that, downstream process in it that measures software and hardware reliability and develops the control measures. All right, so we treat CCF like any other problem. It's a reliability problem. And so we're trying to increase the reliability. And so as we go through these processes, the techniques used to improve reliability address CCF, software and hardware. And humans too, by the way, they all have common cause failures.
Okay, let's see, I guess I'll ask another question. Can you think of how ANS in the standards arena can contribute to the developments of this modernization approach that you're addressing, for digital INC? ANS primarily deals with systems and functions, and so it seems like as part of the systems engineering approach, there should be standards that ANS produces that would help designers of digital INC. So just wonder what your thoughts are on that.
Well, I said earlier that our research, when we see what's being done in transportation, aviation, the other process industries, they've left nuclear behind in this area. We don't see any real need for detail or system things that deal with the internal workings of a PLC, for instance, or network, because those things have been done by other people already. IEC 61508 61511 are very powerful processes. There's a few others that are used. We think that those should be used and move on from the quote unquote nuclear INC standards that seek to do duplicative things, because there's a question about how likely is that nuclear will improve the software engineering design standards to address all that we're not. It's already been done. 61508 and the constraints they have in it, we've proved with billions of hours of data that we pulled that problems at the platform level have been solved. Now you can put a CCF into the system at the application level just by being stupid, pardon my French, but that's something that can be reviewed out at that level because it's out where you can see it, and it is where it interfaces with the rest of the plant. So, this is a multifaceted thing. So I think what ANS can do is, one, become familiar with these INC standards that are not inherently nuclear, and look to see how you can do overlays. For instance, today, if I were a practitioner and I was going to use this process, and I was sitting on a standards committee, I would look to create a input schema for IEC 61511 that address nuclear needs at the system and policy level. I wouldn't worry about the inner workings of the PLC and the microchips or the software, the system software. I would worry about the application software, how that's put together to make something do a specific thing in a nuclear power plant.
Okay, let's see. I don't see any other questions. So I want to thank you, Matt, for your presentation. And, I look forward to people offering, any other comments that you may have, after the presentation. But for now, I appreciate your presentation, and I appreciate the people who have taken the time to participate in this community of practice session. So with that, again, I want to